Welcome to the Explainer. Today, we're diving into Chapter 4, specifically Topic 4.2, where we're going to peer right under the hood of the invisible machinery that powers, well, almost every modern application you use. We're talking about database storage engines, because every single time you like a post, save a document, or query some massive dataset, you're relying on a deeply complex architecture that's making split-second decisions about exactly how to store and retrieve your data. Millions of these operations are happening in the blink of an eye. And these tiny, invisible choices, they literally dictate whether a system is going to scale globally or just completely crash under pressure. So we're going to break down the two absolute heavyweight paradigms dominating the space right now, B-trees and LSM-trees.
Okay, let's lay out our roadmap for today. We'll start with the invisible engine, move into log-structured storage, then check out the B-tree standard, followed by the heavyweight matchup between the two, and wrap up with a summary and takeaways. Let's get right into it.
Section 1, the invisible engine and the core conflict of databases.
To really understand why these entirely different storage engines even exist, we kind of have to start with the fundamental tension at the heart of all database engineering. It's this constant tug-of-war between two opposing forces. Just think about it for a second. When your application says, hey, save this, how does a database actually remember it so you can find it again instantly among, say, terabytes of other information? Well, the absolute simplest way to save data is just to append it to the end of a file, right? It's incredibly fast to just dump data at the end of a long list. But if you do that, finding it later means scanning that entire file from top to bottom. In computer science, we call this an order n operation. Imagine trying to find one specific receipt in a massive, totally unorganized box of millions of papers. You'd have to look at every single one until you found it. And for a global application, that is a complete nightmare. It's unsustainable. So, to fix that, we use indexes. These are extra data structures that act like signposts, telling us exactly where our data actually lives. But here is the inescapable trap of database design. Well-chosen indexes will dramatically speed up your read queries, absolutely. But every single index you add is going to slow down your writes. Why is that? Because every time you add a new piece of data, you don't just write the data to the disk once anymore. You also have to do the extra work to update the index. You're forcing the CPU and the disk to maintain multiple signposts. So there's no perfect, magical solution out there that gives us infinite read speed and infinite write speed all at the same time. There are really only optimized engineering philosophies based on what your specific application needs more of. You are always trading read performance for write performance, or vice versa.
Moving on to Section 2, log-structured storage, or LSM-Trees, the append-only contender. That brings us to our first major architectural philosophy, log-structured storage, which you'll usually hear called LSM-Trees. Now, this approach is highly optimized for systems that need to write data incredibly fast. And the foundational concept here is actually brilliant in its simplicity. If you want blazing fast writes, the best way to do it is to stick to that original idea of just keeping an append-only file, kind of like a running diary or a system log. But to avoid that slow read time nightmare we just talked about, we keep a hash map in the computer's fast active memory. This hash map simply links the key, let's say the number 42, directly to the exact byte offset on the hard drive where that data lives. So if you want to read key 42, the memory tells you, hey, jump straight to byte 60 on the disk. It's incredibly fast. But there is a massive catch here. At enterprise scale, you can't possibly keep an index of every single key in your computer's limited RAM. You'd literally run out of memory in no time. So how do we solve this RAM limitation? Well, engineers developed this concept called the S-table, or sorted string table. Instead of just appending data totally randomly in the order it arrives, what if we ensure the file saved on the disk is strictly sorted by the P? This creates a really elegant solution. Because the file is alphabetically or numerically sorted, you no longer need an index entry in your memory for every single key. Instead, you can create what's called a sparse index that only tracks the first key of every block of data. Think of it exactly like a physical dictionary. You don't need a table of contents that lists every single word in the book. You just look at those guide words at the top of the page. If you know the word you're looking for falls alphabetically between the two guide words in your sparse index, you just jump straight to that block of data and scan the very short distance to find your exact record. It saves a massive amount of memory. But this raises a huge mechanical question, right? How do you write to a sorted file efficiently without having to rewrite the entire file every single time a new piece of data comes in? Well, here is the clever life cycle of an LSM tree. Step 1, incoming writes don't actually go straight to the hard drive. They go into a fast, temporary memory structure called a mem table. Think of this mem table like a physical notepad sitting right on your desk. Because it's in memory, it can sort the data instantly as it arrives. Step 2, when that notepad gets full, usually after a few megabytes of data, it gets flushed to the permanent disk as a brand new, completely immutable SS table segment. Think of this as ripping off a full page of your notepad and filing it away into a permanent filing cabinet. And then step 3, when you need to read a key, you check your active notepad first. If it's not there, you check the newest segment you just filed away, then the next oldest, and so on. Now, over time, flushing all these mem tables is going to create a ton of separate segments on your disk. Having to check hundreds of different segments would eventually make reading painfully slow. To solve this, a background process called compaction steps in. It's very similar to the famous merge sort algorithm. The database reads these sorted segments side by side and smoothly zips them together into a new, larger segment. Because both files are already sorted, the database just looks at the first item of each file, copies the lowest one over, and repeats. Now, if the same key appears multiple times across different segments, meaning someone updated a record, the database resolves that overlap by only keeping the most recent timestamp. It just throws away the old, obsolete data, which keeps everything clean and frees up precious disk space. But wait a second, if everything is strictly append only, and those segment files are immutable, how do you actually delete a record? You can't just go back and erase it. Actually, scratch that. You literally aren't allowed to touch that file once it's written. Instead, you append a special deletion marker. It's morbidly, but very accurately, called a tombstone. When that background compaction process is merging segments and it suddenly encounters a tombstone, it knows to completely discard any older values for that specific key. Now, it's really important to realize that the tombstone itself actually takes up space on your disk until that final, deepest compaction pass happens and fully erases the data. That's a pretty key technical trade-off of this whole append-only philosophy.
All right, Section 3, let's talk about the B-tree standard, the update-in-place champion.
So let's shift our focus to the second contender here. This is the reigning champion of the database world, honestly, since about 1970, the B-tree. While log-structured storage is super popular for certain modern high-throughput systems, the B-tree has really stood the test of time. It remains the standard index implementation in almost all relational databases. And B-trees take a completely different architectural philosophy. Instead of variable-sized append-only segments, a B-tree breaks the database down into perfectly fixed size blocks, or pages. These are usually 4 to 16 kilobytes in size. Why that specific size? Well, because it maps directly to the underlying architecture of your hardware. Operating systems and disk drives naturally read and write data in these exact fixed-sized chunks. And crucially, instead of appending new data, a B-tree modifies these pages by overwriting the data right in place on the disk. To find data, these pages are structured into a highly organized tree format. You start at the very top at what's called the root page. This page contains boundary keys and references that point down to child pages. So if we want to find key 251, the root page tells us that this key mathematically falls between the boundaries of 200 and 300. We follow that specific reference down to the next level of the tree. And we just do this again, jumping down the branches until we hit the leaf page at the very bottom, which contains our actual target value. This tree is meticulously balanced. That means every single leaf page is the exact same distance from the root. Because of this perfect balance, looking up any key, no matter where it is, requires a very predictable, very small number of jumps. This makes read times incredibly consistent. But what happens when we want to add new data, and a fixed size page is completely full? We can't just expand the page because remember, its size is strictly fixed to match the hardware. Well, the B-tree handles this by splitting the page. If we want to insert, say, key 334 into a full page, the database basically splits that page right down the middle into 2 half-full pages at a boundary key, like 337. It takes half the data for the left page and half for the right. It then travels back up the tree and updates the parent page above it with a new boundary reference to point to these 2 brand new children. This constant splitting and updating is exactly how the tree remains perfectly balanced as it grows over time. Now, overwriting a page perfectly in place on a disk is inherently dangerous. If the database crashes or loses power exactly in the middle of a physical disk overwrite, you are left with a corrupted, partially written file. In the industry, we call this a torn page. Your database is suddenly broken. To protect against this, we encounter one of the most fascinating ironies in database engineering. B-trees are fundamentally designed to avoid the append-only log philosophy, right? Yet, to make them safe from crashes, engineers had to give them an append-only log. It's called a write-ahead log, or WAL. Before the database is ever allowed to overwrite the actual tree page, it absolutely must first append the change to this log. If a catastrophic crash happens, the database just reads the WAL upon reboot and restores the tree back to a healthy, consistent state.
Section 4, the heavyweight matchup, comparing the trade-offs. Okay, so we have LSM trees that append data and merge it later, and B trees that organize data into fixed pages and overwrite it in place. It's time for the heavyweight matchup across a few key performance battlegrounds. The first battleground is just pure physics, how these engines actually interact with physical storage hardware. LSM trees write in large contiguous blocks. We call this a sequential write. B trees, because they update specific pages anywhere in the tree, perform small, scattered overwrites all over the disk. We call these random writes. Now, on a hardware level, sequential writes are vastly superior. If you're using a mechanical hard drive, a random write means a physical magnetic read-write head has to literally swing across a spinning platter to find a new location. But even on modern solid-state drives, sequential writes are faster because SSDs have to erase large continuous blocks of data at a time. This physical reality is exactly why LSM trees can sustain a much higher write throughput. But to truly understand the performance limits here, we have to look at a pretty devastating metric called write amplification. This is the ratio of how much physical data the database writes to the disk compared to the size of the logical data you actually asked it to save. So imagine you ask the database to save a tiny 10-byte temperature reading. To process that tiny save, background processes might force the database to write 100 bytes of data to the physical disk. Your 10-byte write was just amplified 10 times. In a high-traffic system, this disk bandwidth becomes your ultimate bottleneck. And worse, on solid-state drives, high write amplification literally burns out the physical flash memory cells faster, which adds a tangible, expensive hardware cost to your overall architecture. Both of these engines suffer from write amplification, for sure, but the causes are totally different. An LSM tree suffers from amplification because it writes the data to the initial log, again when the mem table flushes, and then again every single time the data is merged during background compaction. A B tree, on the other hand, writes to its write-ahead log and then often has to overwrite an entire 4-kilobyte page just to change a few bytes of data within it. Furthermore, B trees suffer from fragmentation over time. Because pages split and data is deleted, unused holes appear inside those fixed-size pages. To fix that wasted space, the database has to run background vacuuming processes to rewrite and pack the pages together. But generally speaking, LSM trees tend to have lower write amplification, which gives them a distinct edge for super heavy workloads.
Section 5. Summary and takeaways. Choosing your engine.
We've covered a lot of deep engineering mechanics here today, from mem tables all the way to page splitting. So let's synthesize all of this into practical takeaways so you understand exactly how these trade-offs manifest in the real world. Think of this as your definitive cheat sheet. At their core, LSM trees append and merge, while B trees update in place and split. Because LSM trees might have to check multiple segment files in the background to find a single record, their read speeds can be slightly slower. B trees, however, guarantee a predictable lightning-fast tree depth for reads. But because LSM trees utilize those smooth sequential writes, their write speed is typically much faster than the random, scattered overwrites of a B tree. Finally, LSM trees tightly compact their data, whereas B trees can become fragmented with dead space, requiring background vacuuming maintenance to reclaim your hard drive.
So the crucial point is captured perfectly by this quote right from our Chapter 4 source material. As a rule of thumb, LSM trees are better suited for write-heavy applications, whereas B trees are faster for reads. It really is that simple. If you're building an Internet of Things system that logs thousands of tiny sensor readings every single second, the append-only speed of an LSM tree is absolutely your best friend. But if you're building a complex financial application prioritizing massive, rapid user lookups, you stick with the predictable, balanced architecture of the B tree. Database storage engines are not magic. They are a careful, deliberate, balancing act of structural trade-offs. Understanding these hidden mechanics empowers you to make the right architectural choices when the stakes are really high. So I want to leave you with this final thought. When you design your next system, carefully consider the hidden storage costs of your software. Are you optimizing for the highly predictable, structured memory of the past or the relentless append-only speed of the future? Thanks for joining me on this explainer, and keep building.